Hello everyone, Ross Satchell from Microchip Technology again. Today we're taking a look at the Q43, which is a new group of devices in the PIC18 family. This video goes over the project in the application note AN3381, brushless DC fan speed control using temperature input and tachometer feedback. One of the things that makes this family of devices stand out is that it has a 16-bit PWM peripheral versus the usual 10-bit peripheral found on most other devices. Before we go into what this means, let's first go over some PWM basics. PWM is most often used to fade LEDs and control the speed of DC motors, as well as control hydraulics, power supplies, heating elements, and much more by varying the average output power to those devices. This is achieved by altering the on-time width or duty cycle of a train of pulses. For example, if you had a 5-volt output with a duty cycle of 20%, then the average voltage would be 5 volts multiplied by 20%, which is 1 volt. So then why is a 16-bit PWM better than a 10-bit PWM? As mentioned earlier, many microcontrollers have a 10-bit PWM module, which is able to output up to 2 to the 10, which is 1024 discrete widths. However, a 16-bit PWM module is able to output 2 to the 16, which is 65,536 discrete widths. So a 16-bit PWM module yields up to 64 times the resolution of a 10-bit PWM module. This increase in resolution decreases the step size between power levels, making it much easier to control your output device, such as a motor, with exactly the power level needed for your application. You may have noticed I said up to 64 times the resolution. What does that mean? As a PWM peripheral's base frequency is increased, the resolution possible from that PWM peripheral decreases. So it's important to know approximately what frequency you'll be running your PWM peripheral at so that you don't have any unexpected problems with PWM resolution when you are developing your project. So now that we've covered PWM basics, what other peripherals is this project using? It is using ADCC, which is analog to digital converter with computation, CCP, which is compare, capture, PWM, and UART, which is universal asynchronous receiver transmitter. So let's go over them one at a time using a block diagram of this project. So what is the ADCC? The ADCC is an analog to digital converter with computation. It has built-in computational features that provide post-processing functions, such as oversampling, averaging, and low-pass filtering. In this particular project, the ADCC peripheral is being used in burst average mode. In this mode, a single ADC trigger event causes the ADC to accumulate samples until the number of samples matches the value in the ADC repeat setting register. Then the accumulated samples are averaged and the temperature is calculated using the simplified beta parameter equation shown on page 13 of the app note. Now that the temperature has been obtained, the fan speed can be set. This is done using two peripherals, PWM and CCP. A typical DC fan uses PWM for speed control. However, in this project, we are using 4-wire DC brushless motors. These have the usual power and ground wires. They also have a PWM input and a tachometer output. Each fan has 2 embedded magnets so that when it rotates, it gives 2 pulses per revolution via the tachometer wire. This tachometer output is routed to a CCP peripheral, one for each fan for a total of 3. So what is the CCP? CCP stands for Compare, Capture, PWM. The CCP peripheral can be set up in Microchip's Code Configurator, MCC, to operate in one of 3 modes. Compare, where it acts like a programmable comparator. Capture, where it's configured with a prescaler to detect rising or falling edges and captures the value of the timer 1 peripheral each time the relevant edge is detected. Or PWM, where it outputs a pulse width modulated signal. In this demo, the CCP is operating in the capture mode where it is used to measure the fan speed. By comparing the time between pulses, the fan speed can be determined. If a given fan is running too fast or slow, the PWM output to that fan is decremented or incremented in a basic feedback loop. As mentioned earlier, the PWM peripheral has up to 16-bit resolution, making available up to 65,536 discrete levels of power to each fan for precision control. in this particular case, cooling for thermal applications. Finally, the measured temperature and the speed of each fan is written via the UART to display the data in a serial terminal. I am using Data Visualizer. So now let's take a quick look at the demo project in action. On the right side there are two coffee mugs, one large and one small. The large one contains hot water and the small one contains cold water. So now let's see what happens when the thermistor is placed in each mug. If the temperature is below 20 degrees centigrade, the fan speed is set to the minimum value. If the temperature is over 70 degrees centigrade, then the fan speed is set to the maximum speed. Otherwise, the fan speed is determined by the temperature detected by the thermistor. All three fans are controlled individually by their own dedicated PWM output. Now let's take a deeper dive into the PWM peripheral. The Q43 has three 16-bit dual PWM modules. Each module has a single output slice, which is composed of two PWM output channels. The two channels in a given slice share both the PWM frequency and the alignment and compare mode. However, each channel can have different PWM duty cycles. In this project, the left align mode was used. So what's up with the different alignment modes? It's been shown that symmetric, also known as phase correct or center aligned PWM signals, generate fewer harmonics in the output voltages and currents. This makes center aligned highly advantageous when using actuators or three-phase motors. Previously, symmetric PWM signals involved more complicated use of timer and counter overflows. As a result, it was much easier to do left-aligned PWM, which just counted down and reset at 0, a timer used for determining duty cycle, to change the PWM state, and then started the timer based on another timer running at the PWM frequency. However, now with the core independent peripherals, the user can easily set up different PWM alignments and frequencies in the microchip code configurator, which is an easy-to-use graphic user interface. Also, driving large numbers of LEDs using center alignment can prevent large current spikes because all of the LEDs are no longer switching on at the same time compared to the traditional left alignment. So we can see that the Q43 has not only significantly increased PWM resolution for your next project, it has also greatly simplified setting up and using multiple PWM outputs, which will serve to reduce your development time for your next project. Don't forget to smash the subscribe button as well as click the bell to be notified of new videos. If you like this video, please click like or leave a comment. Thanks for watching.